Welcome to the Tom Nelson podcast. I have Dr. Michael Connolly here today. He is the father of Ronan Connolly, one of my podcast guests last week. Michael, could you introduce yourself, please?
Okay, well, as you said, I'm Michael Connolly. Not only am I the father of Ronan Connolly, but I'm also the father of Stephen Connolly, Orla Connolly, and Leona Connolly. And they're all PhDs as well. So there you go. My wife's a PhD as well. We're a family of doctors. So.
And you're in Ireland right now as we speak, right?
Yes, indeed. And you can look out the window there, seeing it lashing raining. We have a saying over here in Ireland that if you look out and can see the mountain in the distance, it's going to rain. And if you can't, it's already raining.
We were talking beforehand. You have a lot of good stuff to show us. So let's jump right in there, I think.
Yes, well, what I'll be showing is a lot of new stuff. It's all empirical sort of stuff. In other words, it's not based on models. It's not based on any of my opinions or anything else like that. It's just analyzing data that has been available for a long time now. But new data is coming on stream all the time. So you constantly hear people saying things like, we have only one world and we can't do experiments with it. And that's just not true. We have been, every day we do thousands of experiments on the Earth's atmosphere as well as on the Earth. But let me give examples. The every day currently from 800 stations around the world, you have these weather balloons, which are called radiosondes. They're a balloon. This is a weather balloon. And what it is basically there's a little thing called a sounding or sound on the bottom of it. And they're released out into the atmosphere, generally all around the world at the exact same time, 12 o'clock Greenwich Mean Time and 12 at night Greenwich Mean Time. And there's some ones that do them at 6 o'clock in the morning and 6 in the evening as well. But throughout the world, from 800 stations, they're released at the same time every day into the atmosphere. And they go up about 35 kilometers. And they, on their way up, they record the temperature, the pressure, the height that they're at, the direction of the wind, and the amount of water that's in the atmosphere. And these are all collected and stored in different places around the world. The ones I'm using are stored by NASA, by NOAA, but they're available for everybody to look at. So all of the stuff that I'm going to be showing you here, anybody would be capable of downloading these and doing the same analysis as I have done. So there's nothing strange about this. If you can operate an Excel sheet, you can get these self-same results that I've got. Now, the results that I'm going to present here, we published there about 6 or 7 weeks ago in this first lot of work that I'm going to explain. And the second lot of work that I'm going to go through, we published last year in the peer review processes. So these are all gone through the normal scientific peer review procedures and been published in reputable journals. So this isn't just off the wall stuff, right? So, but what is shocking is the new findings that we have, totally unexpected, and it's going to total head scratcher for a lot of people. An awful lot of models and that sort of stuff are going to have to be reconsidered as a result of these results. So let me probably I'll go through this summary of this first paper that was published there a couple of weeks ago. There was 5 of us or 4 of us, I think, but the lead author in this was my daughter Orla, right? Ronan was a co-author and Willie Soon's a co-author on it as well. So if you look, this is a weather balloon. It floats up through the atmosphere, and this is so that was just showing after the war when they started doing this in earnest. So we have records going back 70, 80 years, and some of them going back even 100 years. But this is the sounding device, typical one that's used. It has a little battery on it. which you plug in, and then it has sensors for humidity, other for wind direction, temperature, and pressure, and so on. And then some of them also have a little GPS device attached to them to independently locate the height and location of them. So they've got extremely good, they're coming up in quality and quantity. The first radio sondes might have only managed to get up 5, 6, 10, 20 kilometers. Nowadays, it's not unusual for them all to go up to about 35 kilometers. And what I will be talking about in this paper is a particular set of very high resolution radio sonde data. They're called ozone sondes. And these ozone sondes take readings about every second. So they take a reading about every 5 meters. They travel up at about 5 meters per second. It takes about 80 minutes to reach 35 kilometers. And all the time they're sending back all of this data and this information, which tells us an awful lot about the atmosphere and what's going on. And because these are so accurate, all the ones up until now, the standard radio sondes might only send you 100 pieces of information back. These send back thousands of readings. So, but there aren't that many of them. The ones that I've been analyzing now these are only sent up about once a week, and there's only 5 or 6 locations in the world where they send them up. But because there's such a high resolution and such accuracy, they allow us to do and look at the atmosphere in a detail that hasn't been available to now. And it's a result of this high resolution and this detail that these shocking results have come out. And they are quite shocking and quite unexpected. And they have a lot of implications for the current narrative of how the atmosphere behaves. But like I say, anybody now can download these data. We give you NOAA's station for them, and you can look at them, and you can look at them yourselves. So what I'm presenting here is not opinion, it's not models, it's actually just looking at the results of these experimental sondes that were done. First of all, I'll summarize, I'll just reduce the size of that a little bit so they can fit it all on the one page. There you go. So with all the radio sondes, the weather balloons, I call them weather balloons, I suppose, that have been sent up over the years, by about the 1970s, a general picture of the atmosphere was coming out, and this was defined for people studying the atmosphere, but also for airplanes and that sort of thing. So this is called the US Standard Atmosphere, and it's been used by everybody now for, as you can see, nearly 50 years. And what has been discovered, I'll just go through this just to explain. I have also got to bear in mind that some of your listeners may not be actually seeing this video, so I'll try and describe it. So what you see is the atmosphere is divided into what's called the troposphere, which is close to the Earth. It's the first 10 to 15 kilometers of the Earth's atmosphere. And it's characterized by the temperature drops off as you go up through the atmosphere. So as you go higher and higher, if you climb up a mountain or various things like that, for every kilometer you go up, you lose about 6.5 degrees centigrade in temperature. For American audiences, that's about 7.3 degrees Fahrenheit per mile, right? So as you go up through, so if you look at Mount Everest there, you can see that's 5.5 kilometers or about 5.5 miles. So it's frozen by the time you get to the top of it. And also the atmosphere is only about half as dense as it is down at the bottom. But the next, up until the middle of the last century, or the early bits of the last century, people could only measure the atmosphere at ground. Now, if they wanted to see what was happening as you went up through the atmosphere, you had to climb up a mountain. A lot of the experiments in the early analysis were done by climbing Mount Blanc in France, so in the Alps. So that was about 4 kilometers high. So a lot of the theories that were brought out then were based on ground-based measurements. A little later, I'll be talking about the circulation models, and that were put forward by Hadley and Farrell and all those in the 18th and 19th century, which are still in use today. But in our second paper that we'll be discussing, again, a shock is going to come there as a result of this new analysis. But we'll get into that in about half an hour, I suppose. But anyway, what I'm saying is in this diagram, you can see we have a little balloon showing the balloon's going up to about 35 kilometers. That includes about 95% of the atmosphere. And so basically what happens is as you go up through the atmosphere for the first 10, 15 kilometers, the temperature drops off and gets colder and colder until it hits suddenly at an area called the tropopause. The temperature stops getting colder, and instead it stays steady or starts to get warmer. And this was a puzzle for people, and people wondered, why was this the case? Because the reason that the atmosphere gets colder as you go up is that the molecules are trying to escape, but are being held in place by gravity and so on. So in order to rise up in the atmosphere, they have to do work, and that makes them colder. So the reason that the higher up you go is the energy used to get the molecules up to that level in the atmosphere has taken thermal energy away from them. I'll discuss this a little detail later on, but this is just giving you a broad picture of the atmosphere. So as you go up through the atmosphere, you hit the tropopause. And this was a puzzle for people at the beginning. They wondered whether or not it was instrument failure or things like that. But then what they noticed was they had weather balloons that went up but also came down. And when they found that they were getting the same readings coming down as going up, they said, well, it can't be due to instrument failure. So then they tried to come up with an explanation for why we had this tropopause, or this warming area. And the explanation they came up with was this area, as you can see here, when we labeled it in, is an area where there's a lot of ozone. In the sense that it's, I'll go into the ozone a bit later as well. But ozone absorbs ultraviolet light from the sun. And so what they reasoned was that the ozone was absorbing the ultraviolet light from the sun, turning this into heat, and this was heating up the tropopause stratosphere region. And so that's why that was getting warmer. And the stratosphere, because it was closer up to the sun, was getting more heat and getting warm for that reason. But what we have looked, and that's the current explanation that's still given by a lot of modelers on that, to why the tropopause exists. But as a result of our investigations using the radiosonde data and the ozone sonde data, we found that there are a number of problems there, not least of which is that you get these tropopauses and the most amount of heat occurring in the Arctic regions and the polar regions in the winter, when there's no UV light at all, it's dark. And so that is a problem. So in order to overcome that, people called Dobson and Brewer came up with these ideas where they said the ozone was being circulated to the poles by what was called Brewer-Dobson circulation. Again, this was all a theoretical notion, no experimental evidence for it or questionable stuff. And what we've shown in our second paper is no evidence at all for these sort of circulations. But again, I'll get into that first. So when you look here, this is an ozone sonde from Boulder, Colorado. I've just randomly picked it 13th of October 2016. And what it shows here is as you go up through the atmosphere, you can see how the pressure drops off with time. So the bottom scale here is time. So you can see it takes nearly 5,000 seconds to get up to there, which is about 80 minutes. So what these ozone sondes go up, and then they're filled with helium. And when they get up to what they think is a high enough level, they let some of the helium out, and so they come back down again. So we get measurements going up and coming down. And you can see the standard definition that of the tropopause that the World Meteorological Society came up with in 1952, I think it was, and is still used today. But again, it was based on poor resolution data, and I mean poor by today's standards. In their day, they were the best you could get, and for a long time still were. So their definition was based on very sparse readings. In other words, one every kilometer or every 2 kilometers sort of things. You know, they weren't very close together, not the 5 meters apart that these ones here are done with. So their definition was when the temperature, when the lapse rate, the rate at which the temperature dropped off, in other words, 6.5 degrees per kilometer, if that dropped down to being 2 degrees per kilometer for a period of more than 1 or 2 kilometers, then they would define that as the tropopause. And the reason they said for more than 1 or 2 kilometers that it had to be below that was that when you get clouds and rain and that sort of thing, you can, for short intervals of maybe half a kilometer, you can get drops in temperature due to the rain, or rises in temperature due to the rain, and so on, and due to clouds. So they were saying once you get above that bit where the clouds cause problems, then that was the definition. And so in all these radio sondes, or ozone sondes that you can see, NASA have, or NOAA rather, have done the estimate of the tropopause. And that you can see there, that dotted line that we have, that's NOAA's estimate for these ozone sondes of the tropopause. And it's very close to what's, we'll discuss that in a minute. But what's interesting here is that the only one that they are concerned about is the temperature. So you can see there, temperature is falling off, and then it pauses. It then falls off a bit more, but then starts increasing. So I will zoom in on that so that you can see there. How's that? So you can see the temperature there. You can see it's this bottom scale, by the way, is in degrees Kelvin. Degrees Kelvin is absolute temperature. It's 32 degrees Fahrenheit, minus 32 degrees Fahrenheit, 0 degrees centigrade is the same as 275.15 degrees Kelvin. So, but Kelvin is absolute temperature. It's the one used by all scientists when they're, and atmospheric scientists. Some people use centigrade because it has the same width, but the Kelvin is the standard temperature. But what we know, what we've been looking at also, it's not just the temperature, but we've been looking at the water content and the ozone content. Now, there have been other people who have suggested that you could use different gases as a way of determining the tropopause as well. They called it a chemical tropopause. And then there's others who've been using models to calculate the things. But the trouble with the models, or the reanalysis as they call them, is that you can't do it with just one radio sonde. You have to have hundreds of them and so on. So now let's see. Now, what we've done is we have taken those readings and that graphic of the showed, and we can do different calculations on them. One of the things that we can do is if we can take the temperature and we can look at how the temperature changes as you go up through height. And because these changes are, because the readings are given every 5 or so meters, we can get a very accurate level of the rate of change. And what you can see from this one here, this is the lapse rate with, and it's the more or less instantaneous lapse rate, not an average lapse rate as the World Meteorological definition goes for. So this is what happens. And the first surprise or shocker that comes out of it, as you can see, is that the tropopause turns out not to be a pause at all. In fact, this is where the most rapid oscillations occur in the temperature. You couldn't have determined this from ordinary radiosonde data. This is something that only comes out from these high-resolution ozone sondes. And what you can see there is that as you go up, very rapid changes in the temperature with height. So it's reasonably slow, around 6.5 degrees, all the way up, where you can see these changes occur where there's water vapor. You can see there a big change in the water vapor. So that gave a rise to a rise in temperature. So you can see each of these double blips there correspond to that, and again here. But so you get changes, but it's fairly constant at around 6.5 degrees until you hit the tropopause, and then you get these wild oscillations. This is a shocker, right? This is a total shock. The tropopause turns out not to be a tropopause at all. Averaged over a long distance of a kilometer or 2 kilometers, yeah, it does have an average change of around 2 degrees. But you can see here, it's changing 10 to 20 times what you would have expected looking at the little wibbles and wobbles on the lower end of things. So yeah, this is new. This is a shock, right? So it's a head scratcher now for a lot of the models, because the models don't take this into account at all. And yeah, we're going to have to change our whole narrative or our story there. It's going to need the changing. But the other interesting thing is that if we do the exact same thing with the water vapor, we find that the water vapor, again, as you can see, has. So what we're saying is, if you look at the tropopause, and if you define it at where the tropopause suddenly goes from being relatively calm change with temperature to these wild oscillations, you can see it happens quite clearly there. But then if we look at this thing here, the change in water vapor, we find that that's varying very wildly as well. But then when you hit the tropopause, all the water vapor vanishes. It goes down to nothing. Where's all this water vapor gone? Now, there was an explanation that used to be given, that people knew that the water vapor vanishes at the tropopause, but the explanation they were given, and still do, and still the current one, but what we're showing will show it doesn't hold water, is, forgive the pun, they're saying that in the tropics, up in the stratosphere, or up in the tropopause in the tropics, it's one of the coldest places in the atmosphere. And they're saying that the water all precipitates out there, and that this is due to Brewer oxygen circulation. And so that's why it's not there. But in fact, we'll show that that doesn't hold with the data anymore, right? So it was a useful explanation when we had the limited data that we've had up until now. But now with our new data that's coming in, and with this new stuff, we're finding that that explanation doesn't hold at all. We need to come up with another theory to explain where all the water's gone, right? Now, again, Rona was talking to you about a series of working papers that we did a couple of years ago. And again, people can look them up if you look. We put out what we think is a reasonable explanation there. But again, that's working papers. They're not peer reviewed. So I'm not going to bore you with my opinion there. But this stuff here is peer reviewed. So let's just stick at the moment with the peer review thing. By the way, we hold and stand over everything we said in those papers 7-8 years ago. In fact, all of the new data that we've been discovering and all the advances we're making at the moment with all this better data is only confirming, in my opinion, but again, it's still only my opinion until the scientific community agrees with it. So there we go. So now, oh yes, here is a new variable that we have used that you can calculate from the radiosondes. It's called molar density. So the idea behind molar density is it comes from the gas laws. Basically, the atmosphere is a gas. It behaves like an ideal gas, and it's covered by the equation of state for ideal gases. The equation of state for ideal gases is known as the gas laws. It's a combination of them all. I might come back to this in a second, but here's sorry, this is just showing you the equation of state for an ideal gas. The equation of state for an ideal gas says PV, the pressure times the volume of the gas, is equal to nRT, where N is a thing called the number of moles. A mole is called Avogadro's number. It's a count of the number of particles or atoms or molecules that make up the atmosphere, the gas. It doesn't care about what the weight of the molecules are. Carbon dioxide has a weight of 44 grams per mole. Water is 18 grams per mole. Nitrogen's 28 grams per mole. Oxygen's 32 grams per mole. But for some reason, nature, when it's acting as a gas, when it doesn't care about the weight of the molecules. It only cares about the number of them. So these were, I find that's what nature tells us. So it doesn't matter what your opinions are. That's it. So as far as the equation of state of gases are, it's concerned about the number of molecules that are in a volume, not the type of molecule that's in the volume. So even the heaviest molecules would still behave according to this rule here. So that's called the equation of state of an ideal gas. PV equals nRT. And this is, PV is the pressure times the volume. It's work energy. It's mechanical energy, right? So that's why the units there is in joules. So that says the mechanical energy, PV, is equal to the thermal energy. The thermal energy is the energy that's there in the random motion of the molecules. And that's R is called the universal gas constant. There's units of joules per degree Kelvin. So that's the equation of state of the ideal gas law. And if you rearrange that, you get it by, if I take the V over to this side, and if I take the RT over to this side, then I'd end up with N over V equals P over RT. That's still the equation of state. It's just rearranged in a different way. And the reason I do that then is that N over V is the number of moles that are in the volume, or the molar density, as opposed to the specific density, which refers to the amount of mass. But because the gas behaves only according to the number of molecules and not what their actual mass is, that's why we're looking at molar density here. And this gives us new insights. That yellow line is how the dry atmosphere should behave according to the equation of state for ideal gases. And the atmosphere behaves like an ideal gas. Now, what you'll see is that there is a deviation down here where it's not following the line, because this line is for dry atmosphere. But at ground level, you get a lot of water in the atmosphere, and water behaves differently. It can condense out, and it's at a vapor pressure. So it's not behaving like an ideal gas. It behaves like an ideal gas when it's way above its boiling point, or when its humidity is a lot less than 100%. But where you have clouds or anything else like that, it's not behaving like an ideal gas. So that causes that deviation from the ideal gas behavior at the lower level. But the shocker, and this is a shock, why, when we get to the tropopause, does the Earth's atmosphere stop behaving like an ideal gas of that type, but has a change in slope, and so it now changes to a new equation of state? So you can, so it's behaving like as if the gas suddenly became heavier, and that's a shocker and a head scratcher. But when we look, that's that one there. I'll just go down here. This is a universal sort of phenomenon. This is just to illustrate it. I have taken a whole week of radio songs from, where was this place? Albany, New York, right? So a whole week of them. And you can see that the atmosphere, this is plotting the molar density. And you can see for all of these things, one day after another for a whole week there, you can see that in this mid region here where it's dry, the ideal gas law is followed exactly by every single one of the radio songs. Down at the bottom here, we can see in this region, which is called the boundary layer, by the way, we call the lower region, the atmosphere, the boundary layer, where there's water vapor. So that's where all the climate change, the water, the things take place. So that's called the boundary layer. And you can see here, it's different from the dry atmosphere up above. And you can see there it deviates depending on how much, whether it was raining on a day or dry on a day. On the dry days, it behaves more or less like the rest of the atmosphere. But on the wet days, you can see it's deviating out there at the bottom. I could zoom in on that a bit more if you want to do it. Will I?
I think we're good, I think. Yeah.
Okay.
Either way.
But again, this shocker here, at the tropopause, for every single one of these, the atmosphere all behaves in exactly the same way, but it's now behaving as if suddenly the weight of the atmosphere, the molecules in the atmosphere have got heavier. So this is a surprise. It really is a surprise, and it's going to cause headaches for a lot of the models and the narratives that are out there. But anyway, this is the thing. Those people who thought the science was settled are in for a shock. So I would just go in a little bit more detail, summarizing that paper that we published 3 or 4 weeks ago. Again, it's gone through the peer review process. It's there. It's a standard scientific thing. You can look it up. If you go onto our website in series and look at our publications, you can see that one. This is the one where Orla, my daughter, was the lead author on. You can see this is only summarizing that. But what we have here is these very high resolution. Now, I have to say, these are very expensive experiments to do. Millions and millions of pounds or dollars were spent to try and get this data by NOAA and the various people involved. So what you have is these stations are located in Greenland, Colorado, California, Alabama, Hawaii, American Samoa, and the Antarctic. And again, once a week, these songs have gone up. Now, it wasn't until about 2014, 2015 that the songs were a good enough resolution for people to be able to do the analysis that we're doing here. And not all of these stations were active in 2014. And in 2016, 18, they started to stop maintaining. I think there's only 3 or 4 of them are maintained now because they're so expensive, right? But they don't have them. So we took 2016 as being the year where all of these 8 stations had data for the year. And we analyzed the entire year of this data for these things, looking specifically at the tropopause and how we could identify the tropopause. And so, as I pointed out earlier, this is the data that's been returned by each of these. You can see they give you the ascent time, they give you the height, they give you the temperature, they give you the water content, they give you the ozone content at each of these at 1 second intervals all the way up to the top of the atmosphere. Now, what I've done next is I've just put here you can see the difference between doing these in this first one here is in Hawaii. And you can see the tropopause occurs up very high up in the atmosphere, about 15, 17 kilometers, about 100 or about in those units I'm using there, about 10,000 pascals. Pascals are the standard unit of pressure. So the atmosphere is about 10,000 pascals there, very high up. But you can see, what you can see is that the yellow line goes all the way up to the tropopause, and you can see it stays on the dry adiabatic or the dry standard equation of state line all the way. Of course, down you can see at the lower level it deviates because of the water in the high water content in the tropics. Here, this one was taken in the winter, I think it was in Huntsville in Alabama. And there you can see very little water down at the boundary layer. And then you can see the dry atmospheric lapse rate, sorry, not the equation of state line, the yellow one, you can see it's the black line, which is the experimental data, totally follows that until it gets to the tropopause. And again, then the tropopause data, the experimental data, deviates from that straight line. But you can see that does it much lower. It's at about 200, and it's only at about 12 kilometers up. And it's again about a quarter of an atmosphere. Whereas in the tropics, it's only at about 1/10 of an atmosphere pressure. In Hawaii, that one's at about a quarter of an atmosphere. And then if we look at the one in Greenland, we can see the tropopause occurs there way down at nearly 40% of the atmosphere. Again, down there, because the Hawaii is up on the top of a green mountain not Hawaii, the one in the summit in Greenland, that's quite high up that way radio station, so it only starts at that level. But that's very dry because there's no water there because of the ice. You can see that the standard equation of state, the data follows it exactly. But again, at the tropopause there, which is now much lower down, it's only about 8 kilometers, you can see at that spot the data deviates again and behaves as if it's suddenly become heavier, as if the average molecular weight of the gas has become heavier. And this has nothing to do with temperature. This is because, remember, the equation of state is showing how it should behave with temperature and with pressure. And the yellow line is what it should be doing, and it's not. And this is a shocker. Why is it not? Again, surprise, surprise, and this is it. But again, I would urge everybody, don't take my word for this. This is experimental data available to all of you. Look at the data yourself. We described there how you can look at molar densities, how you can do all that. This is stuff that any competent high school physics student should be able to do. It doesn't require a university degree, so there you go. Anyway, so if we look at this molar density, and you can see there, if we look at that as a way of determining the tropopause, and you can see we can do a few measurements on it that would need you to understand a bit more maths. This is differentiation or whatever. What you can see is if you take Summit, Alaska there, you can see our yellow line there. But again, if we do the rate of change, looking at small increments, these are averaged over a fair distance. But looking at the rate of change, you see this sudden rapid change in the behavior of the molar density. It's kind of like as if you were going up through the atmosphere and suddenly went through a cloud area and then came up again to a dry area and then hit another cloud. There's sort of turbulence going on there, and like you're getting changes of in the density like you would get if you were going through clouds and so on. You probably would have noticed this if you were in an airplane and they would say, we're coming into turbulence now. We're going to move up and down. As the air becomes less dense, the plane moves up and down because it can't be held as well. So yes, so what we're seeing is this huge turbulence occurring at the tropopause. But again, you can see the rate of change is calm, but this is just looking at molar density. I'll show you looking at the different other parameters that we can use. But you can see if you look at the rate of change with height, it behaves in that way there. And if you look at the rate of change with pressure, it behaves that way, right? But again, you can see at the tropopause, this change in behavior. And again, if we look at Huntsville, the mid-latitudes, it's an example. The tropopause isn't as low down, but you can see the change in behavior is the same. And then when we go to Hawaii, you can see change in behavior again is the same. So it's just where it starts to behave is different. In the Greenland, it starts to change at 8 kilometers high. When you've only gone up through 60% of the atmosphere. In the mid latitudes, you've got to go up to 75% of the atmosphere, and then it changes in the same way. And in the tropics, you've got to go up nearly 90% of the atmosphere before you start seeing these changes. But the changes have the same behavior. So this again is another surprise, because people give a different definition for how the tropopause was identified in the tropics. It was called the cold point definition, because at this point here in the tropics is the coldest point in the atmosphere that you can get. So in the polar regions, again, they said the polar tropopause. But what we're just saying is they're all just behave. These metrics, looking at the molar density, will allow you to use the same technique to find the tropopause anywhere in the atmosphere throughout the entire globe. So it's a very powerful technique. And as you can see, it's very informative. And again, it's new, you know. So what I'm looking here then is, again, I will zoom in a bit on that. Okay, so when we're looking at that Boulder, Colorado data, you can see there are 4 variables now that we can use to determine the tropopause. One is the molar density, and we can take that variable and we can find the rate of change. The other one then is the temperature. And again, we can take that variable and find how that changes with respect to height and how it changes with respect to temperature or to pressure. And each of them allows us to identify an exact tropopause. And again, then with the water vapor, we can see it changes very rapidly. Then, as you can see, it falls off to nothing. But then as you go higher up, it starts coming back again. So again, that's another shocker. Why does the water vapor come back? In terms of the cold tropopause in the tropics being responsible, that doesn't work. People have tried to make explanations by saying it's some sort of chemical reaction, but what you'll see later is that doesn't fit with the data either. And then here's the ozone one. So what you can see is the ozone behaves in the same way. So the summary from all of this is, up until now, people thought the tropopause was something that was related to the temperature. And all they looked at was an explanation that would say why the temperature was changing in behavior. And the idea that they came up with was that maybe it was ozone absorbing ultraviolet light and causing the atmosphere to heat up. And that was the explanation. But what we're saying is that's not sufficient. Whatever explanation you come up with has to explain, why is the temperature changing its behavior exactly at this point? Why is the water molecules suddenly vanishing out of the atmosphere to come back later on, happening at this point? And why is the ozone suddenly occurring at this point and happening? And then that's the thing. So now what we're saying is, any story, any narrative that you come up with has got to explain all of these 4 phenomena simultaneously. And all of the current narratives don't, right? all of the current narratives, this data all put together says all of the current data are not adequate to explain the data. They have problems. The data doesn't support them. They were the best that we could do when we had poorer sets of data. But now that we've got this new data coming in, now that we've got much better, we have these new ways of analyzing the things, now we have to come up with a better narrative. And we have to, and what we realize is that the narratives that we have and that we've been using up until now are not fit for purpose, right? That's the bottom line. Best we could do at the time, when you have a limited amount of information, you put the best story you can on it. That's why I'm saying narratives, because it's a story, right? But now when we have better data coming in, we find that story doesn't work anymore. So that's the problem. And again, it's going to take a long time for this to sink in to the different groups, the modelers, the different advocates from different positions. But at some stage or other, they're going to have to look at this data themselves and realize the story and explanation that they gave didn't fit the data. So now you need to come up with a new story. So let's continue on, because there's more. You think that was bad enough? There is more. So anyway, okay. So what I just want to show is looking at these 4 different ways now of determining the tropopause. What we did was we applied that to all of the different stations, the 8 different stations that NOAA did these experiments with, and recorded the data and made available to everybody. And it's brilliant of them to do it and to spend that sort of huge amounts of money on it. It was very important that they did, though at the time I don't think this was what they were looking for. Anyway, so now let's have a look. What we find is we have the different techniques. The ones based on the water, the ones based on the instantaneous lapse rate, temperature lapse rate, the ones based on the ozone rates, and so on. I'll just show you here at the bottom. There's the different ones. So the light gray one is the NOAA estimate built on the old 1952 definition of the tropopause. You can see for a lot of them it tends to be a bit higher than normal. And I think that's because of the requirement that you had to have this behavior continuing for a kilometer or 2. So if there was any flick back and forth, it did. But the other problem with the definition that they give for the meteorological one is that according to that definition, you can get 2 or 3 tropopauses occurring in the one radiosonde, whereas our definitions only find one. So that's it. But you can see that they all go up or down at the same time, except for these ones that occur in the springtime of the year, or the summer, for the standard NOAA, or the standard meteorological definition that NOAA uses. You can see all the others are very highly correlated. So here we have a list of the correlations. This is for the entire year. And what I should go back to here is to show, the one thing you notice is that the tropopause jumps up and down all the time. You can see one time it's down to 400, jumps way up, down, up, down. This is a moving feast. It changes on a daily and hourly basis. So assuming that it occurs as for the standard atmosphere at a given height is a pile of rubbish. It doesn't do that. But of course, everybody knew that, but I don't think people knew the extent to which it varies and why it goes up and down. But there's another bits we'll get back into that in a bit more detail later. So anyway, what you can see here is we have these 4 different independent measurements, 5 different independent measurements of defining the tropopause, one based on water, one based on ozone, one based on molar density, one based on temperature, and one based on NOAA's estimates, which is the old 1952 definition of the tropopause, I think. Anyway, so what you can see is that if we do the correlations with the temperature-based estimates, the ozone, water, and molar density all are highly correlated. And the NOAA estimate is correlated, but not quite to the same extent. It's only about 0.5 as opposed to 0.9. Now, I probably should explain what we mean by correlation. If you have two things that are changing at the same time, if one of them is changing in the same way as the other one, so in other words, if one thing is getting bigger and the other item is getting bigger at the same time, then you'd say they are correlated. If they're changing in exactly the same way, they have a correlation of 1. If one of them's getting bigger faster than the other one, they might have less of a correlation. But if one is getting bigger while the other's getting smaller, then they're anti-correlated. And if they're totally anti-correlated, they have a correlation of -1. So a correlation of 0.9 means that they're mostly correlated. Correlation of -1 means that they're anti-correlated. They go in the opposite direction. But what you can see is that all of those 4 new definitions that we have of the tropopause are all highly correlated. And even the NOAA's estimate is correlated with them as well. So that's the summary of the first paper.
Do you have any ideas off the top of your head what the major implications are for mainstream climate science of these changes that you found?
I do. I'll get into them at the end if you like.
Okay. Sounds good.
The first thing is that a lot of the assumptions that underline the models and our current narrative, our current story of the atmosphere, are going to have to change. The data doesn't support them, right? What effect that'll have on their overall models, I don't know, right? All I can say is they're going to have to change their story. It doesn't fit with the data, right? That's what I can say.
Okay.
Well, I could say more, but that's all I can. As a scientist, I can say that because this is our analysis of the data, which is peer-reviewed and supported by the scientific community. And this is the latest last month's data of these very high resolution radio sondes. And it totally questions all of the assumptions that have been made till now. So if you were relying on the old assumptions for your models or your predictions of climate or various things like that, you're going to have to go back to the drawing board. You're going to have to come up with a story that fits all of this data and then see how that works out. I don't know how that's going to go. I know a lot of people, it might do some people a lot of good, it might do other people a lot of harm. But the bottom line is things are going to have to change. I don't know what you're going to do, but you're going to have to change your narrative anyway. So does that answer the question for you?
It does. Thank you. Yep, that's it.
Okay. So now, what I want to show you is this is the result not of that high resolution ozone sondes that I was showing you that we published last month. This is just looking at the ordinary radio sondes, of which about 800 are launched every day and are still today and are used for weather predictions and everything else like that. So these are huge amounts of data. And what we did here is we picked 5 stations, and I'll show you why those were. And we analyzed all of the weather balloon data for those 5 stations for 5 years. We also analyzed all of the stations for the whole radio, some of them in our working paper where we analyzed over 20 million radio sonde data, but you find it very hard to publish a paper with all of that amount of data in it. So this is just taking 5 representative stations and looking at how they behave over a 5-year period. 5-year period was the last 5 years, basically. So according to the current story, the current narrative for how atmospheric circulation takes place, this is the current narrative. So this if you go to any geography or any climate book or Encyclopedia Britannica or NOAA stations or anything like that, they will show you an image similar to this. So what they have is they say there is these what are called Hadley cells, spiral cells, and polar cells. So there are 3 of these types of cells in the northern hemisphere and corresponding ones in the southern hemisphere. And the current story, the current narrative for climate modelers and for weather forecasters and everything else like that is that what happens is the sun shines down on the tropics and heats the ground up there. And because the sun is shining most in the tropics, that heats up the atmosphere there, and that hot air rises. And as it rises up through the atmosphere, it hits the tropopause, that thing that we were discussing in the last point. And as it's going up through to the atmosphere, it gets cooler and cooler. And when it hits the troposphere, they say the troposphere is warmer than it. So the hot air can't rise anymore because it's now cold air, right? Because it's been cooling as it goes up. Now, what we'll show in our results is this is an assumption and nobody bothered to test it. And our paper, which we published last year, did test this. And again, another shocker. It's not true. Right? But I'm jumping ahead. So what you see here is the tropopause, it's supposed to hot air rises until it hits the tropopause. And there it can't rise anymore because the tropopause is warm. And so it travels north or south, depending on which hemisphere it's in. But it travels that way and it gets colder and colder until eventually it gets heavy and sinks down to the bottom. And then it starts traveling back again in a sort of cycle. So hot air rises, goes north, when it gets to the tropopause, goes north, cools down, falls down, and then as it falls down, it starts to heat up as it's getting more energy from the ground, but it's being sucked this way towards the equator. And then that explains the Hadley cell, as it's called. And then the Farrell cell has it falling down here in the same way, but at the same spot. But some of it gets colder because it's hitting colder ground and gets pulled this way. And that heats up and then forms the Farrell cell. And then you have another one called the polar cell. But the one thing about all of these cells that you can see is that at ground level, the air is blowing in one direction. And at the tropopause, it's blowing in the other direction. That's the theory, that's the story. And the explanation for it is that hot air rises, but as it cools down, it goes towards the poles and so on. This story, as we will see, turns out when you look at the weather balloon data, not to be true. And it's easy to check because a weather balloon goes, not only does it go up through the ground level up to the tropopause, goes up past the tropopause, up here to roughly where the stratosphere is. So it goes all the way up to our outer line there and then comes back down and analyzes the data going up and down. So as the weather balloon's going up and down, we would expect to see the air moving in one direction at ground level, the opposite direction at the tropopause, and in the stratosphere going towards the poles according to the Brewer-Dobson equations. Now, well, what actually happens? Well, before I go into that, I want to point out, when you look at the radio sondes, as you go up, you can see they measure the temperature, and there's the tropopause, as you can see. This is one. I'm taking this as an example. You can see it's from Ireland, and I picked the 17th of March, St. Patrick's Day, because it is Ireland, and I am Irish after all. We have to support St. Paddy. So there you go, anyway. So the stratosphere, the temperature at ground level there, it goes up. There's the tropopause, and there's the temperature pausing, and then the stratosphere is getting hotter. And there's the water vapor, as you can see, quite high, drops off, and then it vanishes when we get up here. And here's the molar density with altitude. That's how it behaves with altitude. We'll show you how it behaves with pressure again in a few minutes. But there's the specific density. So if you know the molar density, you can use the ideal gas laws to calculate what the actual density is. So the molar density tells you the number of molecules that are there. But if we know what the molecular weight of all the molecules are, then we can say the 78% is nitrogen at 28 grams, 21% oxygen at 32 grams, 1% argon at 40 grams. Add them together, we get an average weight of 28.9 grams per mole. And we have the molar density gives us the number of moles. So if we know the molar density, we can convert it back into the actual density, because you take the molar density multiplied by the molecular weight. The average molecular weight gives you the absolute density, or kilograms per cubic meter. So if we know the number of kilograms per cubic meter all the way up through the atmosphere, which we do from the radiosondes, and we get that data from the radiosondes, then we can calculate the mass flux. In other words, how much mass is flowing through a square meter at any spot. How much is flowing north, how much is flowing south, how much is flowing east and west. And so we can work all of that out. So what I've done here is, for that particular radiosonde, we measure the velocity, which these graphs on the left-hand side are showing the velocity. Here's the north-south one. And here on this side, we have the mass flux. Now, the reason that's important, because velocity can be going quite fast, but if there's only a little amount of air, so in other words, if we're up at, say, 200, a pressure of 200 hectopascals, or up 80% up in the atmosphere, the air might be moving fast relative to below that, but because there's only a fifth of the amount of air that there is at ground level, it would have to be moving 5 times as fast to get the same mass flux at the tropopause as you would at the ground level. So that's why it's important to look at the mass flux, not the speed, because you have to take both the speed and the mass into account when you're looking at the total mass flux. And according to the standard narrative of the Farrell cells, and that the mass flux should be going in one direction at the ground level and the opposite direction at the tropopause. And what we can see here for this one from this, that's not the case. You can see north-south, it's going only in one direction. At the tropopause, it seems to slow down. And then up above the stratosphere, it's going in the same direction. So in other words, it's not going north and south at the lower, north at the one direction. Well, this one here is for this particular radiosonde, that's the east-west. This is the north-south one here. You can see it's going mainly from coming from the south. The measure speed in the direction the wind is coming from. So the mass flux is saying from the south. So you can there it is there. So here on this day, most of the mass was traveling from the south. None of it at the tropopause was going back. You know, so that whole theory collapsed for that day, for that one radiosonde. But when we look at them for the whole 5 years for all the radiosondes, it collapses in totality, right? But the other thing is, what you find is that the strange thing is, you can see every day it might be going from north to south one day, and then suddenly turn around and go from south to north. So I've just taken this one here and magnified it a bit just to help explain. So what you can see here is these are what are called mandated pressures. Every balloon, as it goes up through the atmosphere, is required to take a reading at 15 mandated pressures. It takes one at 925 hectopascals, one at 850 hectopascals, one at 70 hectopascals, one at 50, 30, 15, 10, 7, and so on. So I have them here. So what you can see is this is for Spain for the full 5 years, right? And what you can see is that for this particular period, the atmosphere was all blowing that way for all of these suns here. And then if you look in the stratosphere, which I've separated out because it would be too cluttered, I've put them as two separate graphs there, but they're lined underneath each other. You can see in the stratosphere, they're all going in the same direction as well. And then suddenly on a day, they turn around and go in the opposite direction, right? So it turns out that the atmosphere isn't going in these circular cells at all. Instead, the atmosphere acts like a giant pendulum. When the whole atmosphere from top to bottom flows in one direction and then turns around and flows back in the other direction. And it oscillates back and forth like that for 3, 5, 6 or days. It goes in one direction and then comes back again. Why does it do this? Well, nobody has considered it to now. This is new, that this is what the atmosphere does. Even in the last month or two, there have been people going and publishing papers about how the Farrell cells are moving north, or how the Hadley cells are moving relative to each other. They don't exist. The Hadley cells aren't there. The Farrell cells aren't there. This analysis, which anybody can do, but only we've done until now, can show you that that model, based on 120, 30-year-old ideas, when we didn't have this sort of data, doesn't work. The story doesn't fit the data. No, instead, what the atmosphere does is it seems to act like a great big pendulum going in one direction, turns around and comes back again. Why does it do that? I have my theories, but I haven't published them. So at the moment, I'm just saying, this is what it does, right? This is what it does. This is not my opinion. This is the data telling you this is what the atmosphere does, right? It doesn't fit the narrative. You're going to have to change the narrative, right? The story didn't work. The data doesn't fit it. It's dead in the water. At the times when these stories were done, it was a good story. It fitted the data. And so they were valid and so on. But now that we have this better data, we have this new way of analyzing it. We're looking at molar density. We can get masses, all of these sort of things. We now can see the atmosphere and data is telling us that's not what I do. Instead, I'm going like a pendulum back and forth. Now, I will put one caveat there. You can see the ground level one there is different than the other ones, all the other stations. So in other words, in the boundary there, down close to the atmosphere at ground level, that doesn't behave like the pendulum going back and forth. And the reason for that, I think, is that if you look, and I'm not just saying this, I've actually looked at it, so I have reason. This is an educated guess, as it were. What happens is, if you have a stream flowing down along, and if you put an obstacle out into the stream will continue to flow down along. But as it goes by the obstacle, it forms little eddies and comes back forming little eddy currents on the side of the obstacle. And what's happening here is, I think, the atmosphere, the Earth rotating around on its globe, and this atmosphere blowing and going in one direction. When you have these mountains sticking up, they are acting like an obstacle to the stream. So you get these little eddies occurring on the far side. So what I find is, wherever you have these radio songs done on the lee side of a mountain, you'll get strange behavior there. But once you get up above the boundary there, once you get up above the mountains, then the whole atmosphere is going back and forth like a giant pendulum. And that's not me saying it. I'm just articulating what the data is saying. It's nothing personal.
Okay, so, I do have a question here, just to double check what you're saying. I'm just looking up Hadley cell on the internet. Yes. Are you saying that that's completely wrong, or it's mostly wrong, or completely wrong?
I'm not saying that. The data's saying
the data. Okay.
What I'm saying is that diagram that I gave you at the beginning.
Yes. Mm-hmm.
That is the current narrative. That's when you look up on the internet today. Yeah. When you look up NOAA, when you look up all of these, when you look at anyone, this is the story you're giving. But our analysis, using the weather balloon data and using the actual measurements and saying, right, let's see what is the atmosphere doing, that's saying, I don't do that. That story is not right. It's gone. It's dead in the water. Now, there are thousands and thousands of papers have been published assuming that this story is correct. So all of those people are going to have to revisit their data, right? They're going to have to revisit their models. They're going to have to look and say, what's going on here? So I'm sorry. On one hand, I'm sorry for them having to do this, but as a scientist, I'll say to them, you should be excited. Here is new fields to go into. You should be delighted. You now have something fresh and new. I love it when nature slaps me in the face and says my theories are incorrect, because then I say, good. Now I can, maybe I'll find out what's going on. I love to see what's going on, and I like my theories getting dashed down. But as I point out, what I'm describing here, and which we described in this peer-reviewed paper, gone through the peer review process last year, it's published there. You can look it up. And not only that, but you can actually repeat all of this. You don't need a fancy computer. You can do this on an ordinary laptop. You can download the data from NASA or from NOAA, wherever you want. You can do the exact same analysis. You can follow the steps outlined in our paper. You follow them. You'll get the same results that we did, unless I made some mathematical mistake or something else. But if that's the case, not only all my co-authors, but also all our rear reviewers didn't find that flaw. But the other thing is, everybody else that has downloaded these papers, none of them found these flaws either. So, yeah, you've just Googled, you've given the standard story. What I'm saying is, data says, I'm sorry. That was a lovely story, but it's gone. Right? You have to revisit that narrative.
Good.
What the new stories are, I'm convinced now that this is brilliant, because at the moment, when you look at weather forecasts, they're lucky if they can forecast it out 3, 4, 5 days. You know, you can, if you want to be a weatherman, you can go along and say, today's weather is going to be the same as yesterday. And you'll be right 75% of the time. But if you go 2 days out and say, today's weather is going to be the same as the day before yesterday, you'll only be right about half the time. And if you go and say, tomorrow's weather is going to be the same as the day before yesterday, you're more likely to be wrong. So that's just using that simple rule. Now, using all the computers and various models and everything else like that, we have pushed that up from being 75% right, saying it's going to be the same as yesterday. We're about 85 to 90% right, saying it'll be the same as yesterday, or well, what we predicted. But still, if you go out 5 days, you'll find that you're, again, more likely to be wrong than right. And I think the reason for that is that these models are based on these circulation things, which aren't there. But if you looked at the atmosphere acting like a pendulum, if your model's saying it's getting warmer, it's getting warmer, it's getting warmer as it's coming from the south, say, in the northern hemisphere, and then suddenly it turns around and comes back, your models are going to throw out of kilt. You know, so I think once we understand this pendulum effect of the atmosphere, our ability to predict the weather is going to come on in leaps and bounds. If we can find out what's causing these pendulum swifts back and forth, and again, I have my theories, but I don't want to spoil it for everybody, then our ability to predict the weather forecast should go. There is a big motivation now for everybody to look at this new actual data and say, let us actually now get a toast of realism and start looking at what the actual information is telling us, not what our models based on 102, 120, 130-year-old ideas, which were all based on notions that were done at ground level, you know, and when you had to climb up mountains and that sort of thing. So, yeah, what I'm saying is clearly the data is saying that Hadley-Farrell polar cells are not there. Sorry.
Okay.
Don't blame me. Blame all of those hundreds and thousands of people who were sending all those weather balloon data up, making all of those measurements. And I thank them all for the great work they've done. I wouldn't have been able to discover all this. By the way, I do all of this. Why do I do all of this? I'm not driving an agenda one way or the other. I do it for fun. I like knowing what's going on. I'm doing all this. I can tell you, I don't get paid for this, right? I'm doing this free gratis, right? I was born in the first half of the last century. My pension's good enough for me. I don't need money for this. I'm not driving one agenda or another. I'm just looking at the science. I'm looking at the data. I do it because it's fun and I like knowing what's going on. So don't be saying I'm a skeptic or a believer or whatever else like this. I am just looking at the data for my own benefit, but I'm sharing it with you because I like to think that if we're doing science-based policies and that, we should actually base them on science, not on some fairy tale. So what does it mean for all of the narratives and all of the different things that are out there? Again, that's something that, okay. So what I'm saying is, this is the thing. This was the mass flux that I was saying that's actually there. Now, nobody, by the way, nobody has measured mass flux until that paper. That's the first time it was done. You'd say, why didn't anybody do this? I don't know. I don't know what they're getting all that money for. I'm not getting any of it anyway, though I wouldn't mind if they gave me some of it. But beside the point. That's beside the point. If anybody feels like giving money to the Ceres project, do log on to the Ceres site and donate. I don't get any of it, by the way. So Ceres hasn't got enough money to pay people like me. It's just that's life. Anyway, so is there anything else you want me to talk about on that? Oh yes, look, there's the correlations that we've done. So this is Iceland. So what it's showing is that if you averaged over the entire 5 years, and if you look at how the average thing goes, there's in Iceland, it all flows in the one direction. If you look down here, the one place that I will say that the Hadley cell notion had something going for it was in the tropics down here in Mauritania. You can see at this level, the mass on average was flowing in that direction from north to south, but up above 50, it's flowing from south to north. But what it isn't doing is that it does that all the way up to the stratosphere. And if you look at the area under that curve, it's much bigger than it is down here. So yeah, Hadley, by the way, came up with his theory in the tropics. So he did have some evidence going for him, you know. So it's not that they were off the wall. It's just that the amount of data they had wasn't good enough. And then that's the north to south. This is the east to west ones. Again, this available is all online. It's all in the journals if you want to look them up. Mm-hmm. Now here is the correlation, right? As I was saying. So what I've done here is I've taken the mid-atmosphere, mid-latitude, right, and said how is the different mandated levels, how do they correlate? Now, obviously, at 50, which is mid-atmosphere, it correlates with itself to a value of 1. So that's why you have that 1 there all the time. It correlates with itself. Obviously, it behaves like it does. But then you can see here, these down at ground level, not as well correlated, only about a third. And then up in the stratosphere, not as well correlated. But the key point about them all is that they're all positively correlated. They aren't going from positive here through mid-atmosphere and going negative here, which if we were looking at the tropopoles, if we were looking at the Hadley Farrell and so on, that should be the case. They should go from there, 1 to -1 at the tropopause. And it doesn't. It clearly isn't, right? There is not even a ghost of a chance. But as I said here, down in this one region, in this one thing, you can see, yeah, that's negatively correlated, going positively correlated. but it doesn't go that far. This is the Mauritania one that I was showing you the other thing. But there you can see the correlations, and that correlation is run over 5 years, 365 days a year. So it's not just done over a few bits of, it's done over thousands of things. And it's so you can see, the whole circulation models and all of the stories, all of the narratives based on the old circulation models are now going to have to be rewritten. People are going to have to just go back and look at the actual data. Don't look at the story. Forget the story. It's wrong. It's not wrong in the sense. What I mean is it's out of date. It doesn't explain the data. It explained what was going on with people, what they knew 120, 130 years ago in the time of Farrell and so on. But now that we have good data today, and we have it all there, and it's all housed, and we can all analyze it, everybody should, who have any doubts about this, just go and look it for yourself. Don't take my word for it. Don't. I urge everybody to go looking at the data. You know, it's it. Never take any old fogey's word for it. Okay, so that's that. Probably I could give you a summary maybe of one of the papers. Okay, I'll tell you what. There's a paper we put out. There is a paper we put out last year. I think it was last year. And it's an award-winning paper. It was a review of the different types of energy that we use: renewables, coal, oil, nuclear, water, and so on. And what we were looking at was trying to see what we should know about each of these. What motivated us was, at the moment, renewable energy accounts for maybe 5%, in some countries, maybe 5%, but mostly it's only about 1 or 2% of the amount of energy that's being used. But if we're going to increase the renewables up to 50%, say, then we should be looking at what the side effects of that were. If I wanted to increase the amount of fracking I was going to do, for example, or the amount of oil, if I want to put it through a new well, I'd have to do an environmental impact and say, what effect is this going to have on the environment? Well, all these renewables have been getting free passes. So we said, right, we now have to go and look at these renewables and see, do they deserve a free pass? And if they don't, are we prepared to put up with the upsets that are there? Or if they do, are we going to jump and say, yippee, we should all go on board with that? So I'm prepared. I was back in the 1970s. I'm giving my age away now. But I had, in 1974, my wife and I moved back. We had moved to Canada, but we decided, we were expecting our eldest son, and we decided we'd move back to Ireland. And so in 1974, we came back to Ireland, and I started teaching science. And I also started doing engineering and things like that. But I was one of the founder members of the Irish Solar Energy Society, because back in 1974, we were all fearing a great freeze, because Callendar had put forward this notion back in the 1930s that carbon dioxide was heating up the planet. And he had presented that to the Royal Society. But it went down not very well at all. And what they all said was, it's a nice theory and was brave of them to put it forward, but we look and see how it goes over the next couple of decades. But by the 1940s, the temperature was still going up, but then in the 1940s, it started to cool down again. And it started cooling away down till the 70s. So when we came back from Canada in 1974, there was an oil crisis on and petrol wasn't available. We had to queue up for petrol and everything else like that. And I was worried, what's going to happen with this great big freeze? And the New York Times had, world going into a great big freeze, and we're all doomed to die and everything else like that. So I took all that seriously, and I started working on wind turbines. I built windmills and did solar energy and all of these sort of things. By the way, I am a great fan of solar energy. I run a research farm down here where we grow tropical fish, right? And so that's all heated by solar energy, you know. So I'm not knocking solar energy, but are I knocking wind power? I just don't think it's fit for purpose. So what you have here, this paper is energy and climate policy. So in other words, we're saying, look at the different energy sources and how should that impact on our climate policies. So what we did was we evaluated global climate change expenditure. So in other words, how are we spending money tackling global climate change, right? So this is it. Now, what we did was we took the published data from the EU and various places out where and we give the sightings for them, where they actually assimilate and collect all of the different expenditures on different sources of climate change expenditure, as you can see there. So this paper here was published last year, as you can see. It's published in Energies, a good journal, peer-reviewed. As you can see, there was 5 of us authors on it. There was myself, Ronan, Willie Soon, Oisin, Jerry, Coileen rather, and Jerry. Those were the 5 authors. This, as you can see from the metrics, which I downloaded there the other day, has had over 25,000 downloads, not only of the actual full article, but of the reviews as well. And that's phenomenal for a scientific journal. And this isn't a small downloads. There was 70 or something odd pages in it. It was a review article, right? But not only that, we were told a couple of weeks ago, we were told that we've been given a reward for it. We got a prize of 400 euros. We'll have a big party if we can all get together. It'll pay for a meal anyway. But it's not so much the size of the prize, but it's actually been given the prize. But I'm trying to say to you, it's not off the wall stuff. It's peer reviewed. It's been downloaded by, 25,000 people. Nobody has been publish any flaws in it, so you can reckon this is reasonably sound. So what I'm looking at here is this is the actual expenditure for where the money is expended in trying to fight climate change. So what you can see is 33% is spent on solar, 22% spent on wind, 10% spent on other renewables. That's like palm oil, timber, then sustainable transport, turning it over from being driven by gas and oil and that, energy efficiency, that's improving the thing. So the insulation in houses or draft excluders and that sort of things. So what you can see is the vast majority, over 55% is spent on wind and solar. 10% on other renewables, like wind power, timber, waterfalls, all of those sorts of things. Sustainable transport, other mitigation things. So in other words, things like stopping burning carbon, changing your footprint, those sort of things. On adaptation, only 5% of the money. So in other words, what they're doing is 95% of the money is spent on all of these grandiose things. Only 5% of the money is spent on looking at trying to prevent flooding and various things like that. You know, increasing, putting houses in areas that aren't going to cause damage and that sort of thing. So I think that's, my personal opinion is we should be spending more in adaptation than 5%. We should be making sure that people aren't flooded and that hurricanes aren't ruining the housing and various things like that. But that's just my opinion. It's only an opinion. And you're entitled to reject it if you want. And in fact, I think most people do. I don't take offense. Anyway, here's the total expenditure. You might be shocked, right? The total expenditure on climate renewables, this is in billions, 500 billion, right? So what we're saying is in building wind turbines and solar, we're spending 300 trillion or 300 billion in doing these. 300 billion. Now, when someone tells me they're spending money on doing something, when you're spending money, you're giving it to someone. I like to look and say, who's taking the money off you, right? So I'm wondering, who's taking this 300 billion a year off people, right? And the answer is people building solar panels and wind turbines. That's who. They're selling it to you. You're giving it to them. They're making it. Now, you look at any good, decent company worth its salt will spend between 9 and 11% of its revenue on PR, right? So 300 billion, 10% of that is 30 billion. So they're spending 30 billion on their PR for promoting wind farms and solar panels because that's their living. And that's good business, and that's good practice, and that's good. But what can you buy for 30 billion? How much news media? How much radio broadcast? You can buy nearly all of them. And that's why we're only hearing their side of the story, because they're the ones with all the money to spend. I have a few bob. I could afford a cup of coffee with it, but I can't buy a newspaper ad. I couldn't buy one. Anyway, so that just, I'm just showing, that's giving you a flavor of why. So if you believe that all of these wind tunnels or wind farms and solar panels are good and brilliant and clean energy, you're believing that because that's what they're telling you to believe, so that you'll buy these things off them. And it's working. In this country, they're falling over themselves to put up wind. Now, I built them myself, for me, but I reckon they weren't worth the money. So but I use solar for feeding my fish farms and that sort of thing. I wouldn't use wind, it's too expensive. Anyway, but that's beside the point. Let's have a look and see. What I want to zip through is, here is renewables. So of all that money that has been spent out on the renewables, the wind and solar, you can see it has, we're only a small percentage is renewables. And so if we look at what all that money has done for you, it's increased it from about 0.5% over the year to about 2%. So a quarter of a trillion, 250 million, 300 million has only done a tiny little blip on the amount of renewables. That's not sorting out any problem for you. Good luck with that, I'd say. Anyway, the thing is, if you go in to buy a used car off a used car salesman, do you believe what he tells you about the car? Nonetheless, you do have to talk to salesmen. If you want to buy a car, you're going to have to talk to the used car salesman. But the thing is, you use your own judgment. All I'm saying to you is, use your own judgment when you're looking at these wind turbines and these solar farms. Don't take the blurb, the advertising blurb, as read. It's up to you to do your own analysis. Here's some of the analysis that we looked at. That is the demand. Anyway, well, let's see. Here is Ireland, right? I've done a good deal of work here in Ireland. So this was the daily output in demand in Ireland when we did this paper, right? You can see it goes down at night, up there. Sorry, it goes down on the weekends, goes up during the week, and so on. And you can see, you can count the number of weekends there on it for the year. This is the wind generated. We don't have any much solar here. But you can see there are times when there were no wind, right? So this is the output from all the wind generated ones. You can see at times it did do maybe 40%, But the problem is that if you want to have renewables as your main wind source, you need a base load. You need to be able to, when you come in, turn on your light switch and get your electricity to go on. And you need your fridge to operate all 24 hours a day. If the doctor's going in to do an operating on the operation theatre, you don't want him to say, sorry, stop, there's no wind, So that's a problem with intermittency, right? So the two main ones that they're using have huge problems with intermittency. The wind, as you can see, there are whole days when there's no wind. Now, you actually have to have all the same backup there, all the same generating capacity, even if even if you had no wind turbines. So you don't gain on in infrastructure by putting these things in. You just pay for the extra structure. Now, if you look at the solar, this is solar for Ireland. In May and June, we get a fairly good amount. That's amount of kilowatt hours per square meter per day. This is what I use for operating my fish farm. So what you can see there is that we get a lot in the summer when we really don't need a whole lot of it. And in the winter when we need it, we don't get any. So that is a problem with solar as far as Ireland is concerned. And the other problem we have is that we don't get any at night. Yeah, if you go to turn on your lights and you're relying on solar at night, now if you want batteries to do it, then there's problems with the batteries as well. We go into that and we analyze it. But we're looking at all of the solar biomass. This paper analyzes all this is the problems with the lithium and cobalt and so on. There isn't enough to meet the demands. So you have Elon Musk and all those have queues for their sons or for their cars at the moment. And that's because they haven't got the batteries to do it. And nor do we have the batteries to store the electricity. They will tell you that they are coming and they're on their way. But I did a lot of research on batteries as well. You know, I'm a bit of a polymath. But yeah, it's harder than you think. That's all I can say. But I just want to point out some of the things about this is a wind turbine. Now, people say that this is clean energy. Why do they say it's clean energy? They say it's clean energy because it doesn't generate carbon dioxide. Right. So let's dig into that. Here's a wind turbine. And what you do is the wind turbine, the wind blows along, and the mass flux, that mass flux that I was telling you, that's going through the blades, and that's what drives the blades, right? And makes them turn around. But on the lee side of the wind turbine, the wind is going slower because the wind turbine is taking the energy out of the wind. But also it's introduced these eddies into it, right? So you get these mixing going on. So you have the wind going, cool air going, but it gets mixed here. And this is during the day. And during the day, so you've got this colder air up during the day up on top, and that's mixed and made a bit warmer down below here. But at ground level, where the ground heats up during the day, and you have the heating, that it causes circulations there, and that transfers the heat up to here. So that's what's creating the heat here. So even though overall there's less energy in the wind, it cools down the ground during the day, but at night, the reverse happens. At night, the upper air is warmer than the ground level. And these eddies are coming along and they're heating the ground. So on this side of the wind turbine, the ground is colder during the day. So during the night. So during the day, the ground is warmer. During the night, the ground is colder. During the day, the air up above is warm, but it gets cooler, or is cool, but it gets warmed up by the eddies. And during the night, the ground gets warmed up by the eddies. Now, NASA and various people looked at satellites and looked at this is in Houston in Texas, one of the biggest wind farms. And they looked on the lee side for a number of years, watching what happened to the temperature on the lee side of those wind farms. And what you can see is over these 8 years, the temperature rose because the amount of temperature that the ground was heating up during the night was greater than what it was cooling down during the day. And so the net effect was in the winter, you got an increase of about 0.5 degree. And during the summer, you got an increase of that. That was in Texas. There are other ones where it's up to over 1 degree. But now this is the problem. There's two problems here. One is that if the ground heats up, all of the cold-blooded creatures that are there, their metabolism increases. And I've done a lot of research on cold-blooded creatures, on fish breeding and everything else like that. And what I can tell you is that for every degree you raise the temperature of the atmosphere, their environment, you increase their metabolic rate by approximately 14%, 1/7. In chemical reactions, if you increase the first order chemical reactions, if you increase it by 10 degrees, you'll double the reaction rate. But for biological systems, if you increase it by 1 degree or by 7 degrees, you double the reaction rate. So a 1 degree rise in temperature increased the metabolic rate because of all the enzymes and the vitamins and that, it increases it by 14%. So that increase in the rate of respiration of all of the creatures living in the ground gives an increase in the amount of carbon dioxide that's given off. It gives a 14% increase in a 1 degree rise, gives a 14% increase in the amount of respiration given by the ground creatures there. So that has two effects. It increases the rate at which the ground rots, the material in the ground rots, and it gives off biological carbon dioxide. And so on the lee side of the wind turbine, it's true the wind turbine's not generating any carbon dioxide from burning fossil fuels, but it is generating biological carbon given by the rate at which the microorganisms give off carbon dioxide. During the respiration rate, or sorry, the photosynthesis rate isn't affected. The amount of sunlight is what determines that. But once you're above freezing point and that, the respiration doesn't affect photosynthesis as much as it does respiration. So that is one of the things. It's supposed to be a clean energy. So what happens if we put all these wind turbines everywhere? But the other thing that I want to point out is that you're slowing down the wind on the lee side. Now, in fact, there are people who propose that if you want to stop all the hurricanes, we should put a big bank of wind turbines in the Gulf of Mexico and rob all the energy out of the wind, and this will stop all the hurricanes. Now, that's climate change. It's a man-made climate change, and I don't know whether that's good or bad. If you're in the Everglades and relying on hurricanes, it might be good or it might be bad. I don't know. That's not my problem. I'm just pointing out this thing. But here's the other thing is, if you take all that energy out of the wind is colder. Now, if you have humid air and you take the energy out of it, you increase the humidity. What happens when you cool down hot air, hot moist air? It rains. Here is the lee side of wind turbines in Norway. This is one taken in February, and this was one taken when the air was colder than the ocean or whatever it was. And you can see on the lee side of the wind turbines. Will I increase the size of that? Can you see it? Is it clear enough?
It looks good. Looks good.
Yeah, you can see the wind turbines. You can see them here. There's another one. There's another one. Mm-hmm. And way off in the distance, all these effects. Now that is the wake effect. You can see not only are you taking the energy out of the wind turbine, but the next turbine doesn't get as much energy. But also you can see this whole cloud thing forming out and going out. And so what actually happens is on the lee side of wind turbines, you get more rainfall. Now, further downwind, way down, you'll increase the drought level because all this water has fallen out of the atmosphere. So you're causing all of these climate effects. And I know, for example, there was a hospital up here, Letterkenny Hospital, when they put the wind turbines up on the top of the hills, we got sudden flooding of the hospital that never happened before. And they said it was due to climate change. Yeah, but it was man-made climate change. It was the wind turbines. Anyway, that's beside the point. So what I'm saying is these so-called clean energies are not, that's advertising. That's the guy selling, here, buy this off me. It's a nice, clean thing, and fair dues to them. They've done a good job because they're selling lots of them, so anyway, that about sums it up.
Okay. Okay. I know you have to get to your next engagement, but thank you very much. This is really okay. No, this has been fantastic stuff. I don't know if you have any final point to make. Otherwise, we'll go ahead and wrap up.
No,
thank you
it's
so
fine.
much.
Yeah, if you want me to give any other stuff or if anybody gets back at you, I would advise everybody to go and look all of this stuff up themselves. I've pointed the way. I've put the little map and I've put the X saying dig here. You know, there's treasures there. Meteorologists dig there. Everybody dig here. It's treasures for everybody. But the old narratives are gone. Don't rely on them anymore. We need new narratives.
No, I can't wait to see other people dig into this, like Joe Bastardi, et cetera, to dig into this stuff and take a look. So thanks again. Okay. I'm going to go ahead and stop it, but we'll see you next time.
Okay.
Thank you.
Bye.